here is a question that sounds simple. How fast is the universe expanding? It is one of the most fundamental questions in all of cosmology, and we have been measuring it for nearly a century, and we have gotten very, very good at it. So good that two completely independent teams of scientists using two completely different methods, two completely different instruments, two completely different sets of physics, both measured the expansion rate of the universe, and they got two completely different answers. And when every possible source of error was checked and rechecked and checked again across decades of work, both teams confirmed their measurements were correct. Both answers are right, and they cannot both be right. And nobody knows what to do about that. This is the Hubble tension, the quiet crisis sitting at the center of modern cosmology that most people have never heard of. And by the end of this video, you are going to understand exactly why it matters, exactly why it is so strange, and exactly why the people who study it for a living are either very excited or very alarmed, depending on the day. To understand the problem, you first need to understand what we are actually measuring, because the universe is not just sitting there, it is expanding, and has been expanding since the Big Bang. And the rate at which it expands is described by a single number called the Hubble constant, named after Edwin Hubble, who first measured it in 1929. And the Hubble constant tells you how fast a galaxy that is 1 megaparsec away, roughly 26 million light years, is receding from us. And the unit it is measured in is kilometers per second per megaparsec, which is a slightly unusual unit, but it makes sense when you think about it. Because the expansion of the universe is not like an explosion, where things move away from a center. It is more like the fabric of space itself stretching everywhere simultaneously so that any 2 points in the universe are getting farther apart from each other. And the more distance there is between them, the faster they appear to be separating. Not because they are actually moving faster, but because there is simply more fabric stretching between them. Now, here's where the story starts to get interesting, because measuring the Hubble constant is not easy. And astronomers have developed two fundamentally different approaches to do it. And the fact that these two approaches exist is actually the entire reason the crisis happened. The first method is called the distance ladder. And it is a way of measuring distances to faraway objects by building up a chain of overlapping measurement techniques, each one calibrated against the previous one. Starting with the closest stars, where we can measure distances using simple geometry, the way your brain judges depth using two slightly offset eyes, and working outward using increasingly powerful standard candles, which are objects whose true brightness is known. So by measuring how bright they appear, you can calculate how far away they are. And the most important rung on this ladder is a type of exploding star called a type Ia supernova, which always explodes with nearly the same intrinsic brightness regardless of where in the universe it happens, making it an extraordinary distance marker visible across billions of light years. And when teams like the SH0S collaboration, supernova H0 for the equation of state, used this method and pushed it to its limits with exquisite precision, including data from the Hubble Space Telescope and later the James Webb Space Telescope, they consistently found the Hubble constant to be around 73 kilometers per second per megaparsec. The second method is completely different and does not involve measuring individual stars or supernovae at all. It involves looking at the cosmic microwave background, which is the oldest light in the universe, a faint glow of radiation that filled all of space about 380,000 years after the Big Bang, when the universe finally cooled enough for atoms to form and light to travel freely for the first time. And this light has been traveling ever since, and we can detect it today as a uniform microwave signal coming from every direction in the sky, and it is not perfectly uniform. It has tiny temperature fluctuations, ripples of slightly hotter and colder regions that encode the precise physical conditions of the early universe, like an incredibly detailed fingerprint. And by analyzing these ripples, using the standard model of cosmology called lambda CDM, teams like the Planck satellite collaboration can work forward from those early conditions using known physics to predict what the Hubble constant should be today. And when they do this calculation, they consistently find a value of around 67 kilometers per second per megaparsec. 67 versus 73. That difference might not sound enormous, but in physics, the question is never just whether two numbers are different. The question is how confident you are in each measurement, and this difference is somewhere between 4 and 6 sigma, which is statistical language for how many standard deviations the two measurements are apart from each other. And in physics, 5 sigma is the threshold for a discovery, meaning you are so certain of something that the probability of it being a random fluctuation is less than 1 in 3, 5 million. And the Hubble tension sits right in that zone. And both teams have checked their work repeatedly. And the Atacama Cosmology Telescope released its final analysis in late 2024, confirming the discrepancy is real. And the James Webb Space Telescope has provided the sharpest distance ladder measurements ever made, and the tension has not gone away. If anything, it has sharpened. So, What does this actually mean? Because this is the part that starts to sound genuinely alarming. It means one of three things must be true, and none of them are comfortable. The first possibility is that there is a systematic error hidden somewhere in one or both measurement chains, some subtle bias that every team has missed despite decades of checking, and this is the conservative option that many physicists still hold on to, and it cannot be ruled out. But the fact that completely independent methods, different instruments, different physics, different objects, different teams, all keep getting the same discrepant values makes this option increasingly difficult to believe. The second possibility is that the standard model of cosmology, the lambda CDM model, the framework that describes the universe as containing ordinary matter, and dark energy in specific proportions, is incomplete or wrong in some way. And specifically, that something we do not currently know about was happening in the early universe that the Planck CMB analysis does not account for. Perhaps an early phase of dark energy that gave the universe an extra push at early times, or extra radiation species beyond what we currently model. And there are dozens of theoretical proposals along these lines, none of which have been confirmed. The third possibility is the strangest, and the most exciting one, that there is genuinely new physics involved, something completely outside our current framework, perhaps a new type of particle, perhaps a modification to the behavior of gravity across cosmic scales, perhaps a dynamic dark energy that changes over time rather than being a fixed constant the way we currently model it. And recent results from the Dark Energy Spectroscopic Instrument, DESI, released in 2024, provided tantalizing hints that dark energy may not be constant after all, which would be one of the most significant discoveries in cosmology in decades if confirmed, and it would fit neatly into the picture of a universe that is more complicated than our current best model out loud. The reason this matters so much, beyond just being an interesting puzzle, is that the Hubble constant is not just a number. It is a key that unlocks everything else in cosmology, because once you know the expansion rate, you can calculate the age of the universe, the size of the observable universe, the density of matter and energy, the ultimate fate of the cosmos. And if the value we are using is wrong, or if our model for calculating it is wrong, then all of those derived quantities are also potentially wrong. And the careful edifice of modern cosmology that has been built over decades starts to look less like a finished structure and more like a building where someone has discovered the foundation measurements do not agree with the load calculations and nobody can figure out why. What makes this moment in physics particularly remarkable is the convergence of precision. We are not dealing with rough measurements anymore. We are dealing with measurements so precise that the error bars on both sides are tiny and they still do not overlap. And this precision is itself the source of the crisis, because if our measurements were cruder, we could dismiss the discrepancy as noise. But they are not crude. They are extraordinarily refined. And the refinement has revealed a crack in the foundation that cruder measurements would have hidden entirely. And this is actually a sign of how far science has come, that we are now so good at measuring the universe that we can detect that our best theory of the universe does not perfectly describe it. There is something genuinely exciting about living in this moment in cosmology, because what the Hubble tension is telling us is that the universe has something to teach us that we have not learned yet. Some piece of physics that is sitting right there in the data pointing at us, and we can see its shadow in two measurements that refuse to agree. And we do not yet know what cast that shadow. And the moment we figure it out, whether it is a mundane correction to our measurement techniques or a revolution in our understanding of dark energy or the discovery of a new particle or a modification to gravity, that moment will be one of the most significant in the history of cosmology. And the people working on it right now know they are sitting at the edge of something, and the data is better than it has ever been, and the answer is out there. And we just have not found it yet.